Alright, so we have this circuit here. It is a series parallel circuit. As you can see, series, parallel, alright, and series. Again, it is parallel and series. Alright, so let's look at this whole question here. As it first wants us to find the equivalent resistance within the circuit. Alright, so first we evaluate the network, and we see that these two are in series. Alright, and we try to simplify as much as possible so that we can work with other component within the circuit. So first you look at these two, and then you simple using the formula R5 equal R5 plus R6, and that's equal to 1010 ohms. Alright, so now this 2 becomes 5/6 becomes 1010. So 1010 5/6 becomes in parallel with R4. So we're going to find the equivalence of R4, 5, and 6, which is our parallel combination. So that is equal to 1 over R4 plus 1 over 5 and 6. And we found the reciprocal of this value here. And that's equal to 407. Alright, reciprocal simply mean we're going to put 1 over the value of the two resistors divided by 1. Alright, so the next thing is to find the simplified version of 4 and 5 and 6. Alright, as a single resistor. Remember we said these two, 4, 5, and 6 are 407. So 407 is now in series with R3. So R3 in series with 407 ohms are 4, 5, and 6. So these two combination now is added as a series circuit. So that would yield 737. Alright, 737 is the value we get from adding R3, 4, 5, 6. Alright, so these are 737 ohms. Alright, so now we have a single component here in parallel with this R2 here. So 3, 4, 5, and 6 simplified becomes 1 to meet with a single R2 resistor. So we apply the formula here, and we calculate the resistor in parallel. So R2 in parallel with 3, 4, 5, and 6. So that's equal to 1 over R2 plus 1 over R3, 4, 5, and 6. That's equal to 3, 5, 4 ohms, or 354 ohms rather. So now we get these two will break down into a single resistor, right? And then this 354, as we simplified, is now into a series circuit with this 330. So 330, which is R1, in series with R2, 3, 4, 5, and 6. Very simple 5 resistors that broken down into one. Right, so we add these two together, equivalent. So the final equivalent, or R equivalent, is the series combination of R1 and the total that was on the right side. Alright, so Req is now, or R equivalent equal 330 ohms plus 354 ohms, which is equal to 684 ohms. Alright, so this is how we all work these questions. Alright, so this will be the results from breaking down the circuit. Now let's look at this other question here. We have parallel in this section here, parallel in this section, parallel in this section. This combination is quite straightforward, right? Because when it's like this, it's much easier to understand. Right? But never mind, we take it one step at a time. We look at each section and we're going to work on and we're gonna bring it down to a single resistor. So you can draw and redraw and redraw and redraw and redraw and redraw and to get something simple. Alright, so R7 and 8, these two resistors here, we're going to find the equivalent, that is 1 over R7 plus 1 over R8. Alright, so when you work this out mathematically, that would be simplified to 33.1, right? Now let's move forward here. You can see the next part of questions, we find the equivalent for each section. So it was 7 and 8, and we go 5 and 6, and then we go 9 and 10. All right, so these were parallel resistors, but we've broken down from a single unit. So 5 and 6, 32 ohms, 9 and 10, all right, 34 ohms, and then we have 7 and 8, which is 32, all right? And remember, apply the formula, 1 over the reciprocal, 1 over, right, single resistors, all right, plus, all right, all of them, all combined. So always it's the reciprocal of the resistors, or 1 over the resistors, all right? That is in parallel. Then you do the same for all of them. That is in parallel. Reciprocal, just a reciprocal means 1 over resistors, all right? So just remember as you take this approach, right? So it's reciprocal over 1 over R9, 1 over R10, and we do it the same for all the resistors that are in parallel. Alright, so looking at the simplified our simplification here in this bottom section here, we have R1 in series with R2, right? This was taken from this section. So this R1 and R2 in series, we can simplify this. And this one now, R3 in series with R4, is taken from this section. So what we do here is simple, add up these two values, right? And that gives us 100. Give us value, give us 101. Alright? Now what we left back with is the series combination here that we had simplified from the branches that was in parallel. Right? So 5, 6, 7, 8, 9, 10 now becomes 5, 6, 7, 8, 9, 10, which is 99 on this section here. Alright? So we had them up because now they're in series. And we left back with 3 parallel branch. So let's further look at that. Alright, so the parallel branch that we left back with, we call them A, B, and C, right? So finally we see the equivalent resistance adjustment power combination A, B, and C. So REQ equal 1 over 1 RA and 1 over RB, 1 over RC, which is equal to 33.3 ohms. Alright, so that's not bad. We take this approach as it is, as we try to make things much simpler, and we can easily work questions, right? So this is how you find the equivalent resistance in a series parallel combination. Okay guys, that's it. Just gonna get it from you. Alright guys, so say for example we have an equivalent resistance to be found in a circuit like this, and looking at it from the left side, we can see that if the current was coming from R1, then it would have split up at that junction point right here, just before it goes into R5. So current flowing from left into this node, it goes in this direction, right? and it's split at this point as well. All right, so current goes to this point, it goes to this node, it branches off in two directions, R2 and R3. All right, so let's see the series parallel combination, or we'll break down the resistance. All right, so there are couples of interesting things going on here. First, we see some diagonal resistors, and secondly, we see dangling resistors R5, which is not connected to anything. So in an open circuit situation where nothing is connected across one side of a circuit, if the current was supposed to flow in this direction and through these resistors all the way through R4, and there's nothing that cross or connected between R5, all right, and this terminal, it makes it an open circuit. All right, so current need a closed path to flow, so it will only flows at this point, going all the way to this node, and then it will turn around and go back in this direction. Say the supply source was at this point. All right, so if it's don't have any way to go here and around, then it's not going to go there. All right, so that is just one of the rules when it comes to electrical circuit. Current take a closed path, it doesn't go in a open path, there must be a closed path. So this R5, it does not have any existence. It's just going to stay there forever, and no current is going to be used by it. All right, so we say that that doesn't really do anything. So first, diagonal resistors are essentially optical illusions. Current and voltage do not care about the spatial orientation of the component. So we can redraw the circuit in more familiar grid-like arrangement with no change in how the circuit behaves. So basically, the diagonal arrangement here, all right, we can redraw it in this format here. All right, and it's quite simple. You just move resistor different point along this line. All right, so this is on one line, and we just shifted the resistors a little bit further away from the point that is connected. So these two resistors are connected to just one straight line when you look at it from this direction. All right, so that's how we assess it. We just move it a little bit so it becomes more visible. Most of the time when we look at a circuit, we look at it in two forms, series and parallel. And the more easier we can assess it, it is much easier to interpret. All right, so we'll shift it a little bit and let it be a little more understandable. All right, so look at this arrangement now. So this is more how it's going to be finalized, right, when it's simplified. So if I go up, I go to the previous slide, all right, or taking back a look from the previous slides, what we did in this slide was to drop R5, because R5, it does not suit the purpose of the circuit, because if we look at it from the left side, we're saying that the current does not happen to go across, all right, the circuit, and it would have mean that nothing goes to that resistor, so that resistor doesn't serve any purpose. So in order to assess the whole circuit, all right, we say we look at these resistors here because it goes in a closed path and it's have current flowing through it, all right. So until there is connection across the open circuit, then the resistors R5 becomes valuable, all right, or usable in that sense. So we remove that resistance because no current will flow through it. All right. So we're talking about an active circuit where current is flowing. So we only assist these resistors here, which is R1, 3, 2, and 4. Alright? So we can simplify the questions a little bit better so as to allow the resistors to be calculated. Alright, so R3 and R4 can be simplified, and that works out in the series arrangement as 15.6. Alright, series calculation R1 R3 plus R4. Alright, so next thing we're going to look at what we get after we simplify. So this group becomes 15.6. Alright, so now we say this group is in parallel with this R2. Alright, so R3 and 4 in parallel, R2. So let's combine these two now, R3 or R2 and this group here. So work that is a reciprocal of 1 over R2 and the total of the reciprocal of R3 over of 1 over R34 rather. Alright, so reciprocal taking over 1 over R2 and 1 over R3 R4. Now the total resistance is this resistor R1 in series with this group in parallel. Alright, so we already work out this group in parallel, which we call R234, the value to be 1.37. Alright, so now we know what this group is. We can add it, which is because it's already in series with the single resistors here. Alright, so we add R1 to the group, R2, 3, 4, and the equivalent works out to be 2.37. Alright, so this is when you have a more difficult arrangement and you want to make it simple and understandable. Alright, so this is how to work out equivalent resistors. Alright, so it's good when we can find the equivalent resistors because it helps us to find other things.